What's up, guys? It's me again, chemical engineering guy, and I'm happy to tell you that we're going to close this section number 2, with mass balance in combustion. Remember, we are in mass balance introduction, and I divided this this section or this chapter into sections. Section 1, which was theory, and section 2, which is mass balance application. And now we're going to close this with mass balance in combustion. So probably you heard before the word combustion. Hopefully you know what it is. And you have it in cars, you have it in, I don't know, like almost everywhere you see fire, you will have it. In the kitchen, in the process, in many parts you will see combustion. What it is, combustion is essentially just a high temperature, that's very important, temperature, exothermic chemical reaction. So it's a reaction that gives out energy at high temperature. We need a fuel and an oxidant, usually atmospheric oxygen. And this fuel will be usually fossil fuel. And the product is often gaseous product. I mean gas, CO2, water, vapor, CO, etc. And the most interesting question will be like, why do we need to burn? It's because we need heat energy. And why heat energy? Because we need electrical energy, which means we can use electricity everywhere, domestic and industrial applications. And of course, burning means CO2, which is not nice, and CO, which also not nice. So let me show you a little bit about the importance of combustion. We're going to see the heat energy, but only as a concept. We're not going to analyze it in this course. This is typical for for energy balance problems. How much energy do you need, temperature, specific heat, etc. But what we are going to care about is in mass balance. We're going to talk about reactants and products. Reactants, typically fossil fuel, or it could be any fuel, and oxygen as oxidizer. Inerts, they don't react, and this is typically for this nitrogen gas that comes from the air. Now, products: CO2, CO, H2O, SO2. So this, as you can see, almost are oxidized, and the inerts just flow out. Technically not products, but they just go out. And let me tell you the general idea of combustion is you have fossil fuel or fuel, you have oxygen, you oxidize them to form CO2, water, and heat. This is the thing that we're interested, but right now we're going to be most interested in this part, in the mass balance, in the reaction. It's not that difficult, actually. You just need to balance an equation, and that's what we're going to see next. So let's continue, guys. We're going to balance equations. Why? Because it's super important to balance it because of this stoichiometry coefficients. We're going to balance matter. We need to have the equation right. If we have this wrong, or this, it doesn't work. We need to have a good mass balance with a good balance equation. So failing to do this will of course give you a wrong mass balance. And tips for balancing, I recommend you guys balance first the carbon, then go for the hydrogens, and finally go for the oxygen. The thing here in oxygen is that probably you will need to use fractions, so don't hesitate to use them. It's okay, it's alright, it's possible, and actually it's easier. So you're chemical engineers, we are expecting a lot of you, not only to know combustion, but of course to balance the equation. So just do it, it's easy, don't forget it, because if not, we'll be like, wow, he knows a lot of combustion, but he cannot balance an equation. Come on. Now, first example, how to balance it. I tell you carbon, hydrogen, and oxygen. So let's go for it. We have propane. We have 3 carbons here, so let's put 3 here. Now let's go for the hydrogen. We have 8 hydrogen to the left, and then we should add 4 hydrogens to the right. You have 8 here. Then finally you go for the oxygen count. Let's go to the right and count them. It's 3, 6, and 3. No, this should be a 4, sorry. And 4, it's 5. Actually we have 10 oxygen. Since we have 2 here, we just divide and we know we need to multiply by 5. So we have 10 10 oxygen in the left and 10 oxygen to the right. So good, we have our balanced equation. And this is very important because in this case you're telling me that 1 mole will give me 1 mole. And this case is 1 mole is going to give me 5 moles, or at least we need 5 moles. So we are making a mistake by 5 times. And this one is by 3 times, and this one is by 4 times the mistake. So it's a huge error. Please balance the equation. Now let's talk a little bit theory of the air composition. We're going to use air because of course oxygen alone is kind of expensive. We can buy oxygen, typical liquid oxygen, LOX, but the typical oxidant we use will be air. Air is a mixture of nitrogen, oxygen, many gases which are noble gases, and gases that are CO2, methane, hydrogen, water, etc. This is as vapor. I have it here from Wikipedia, the graphic. So as you can see, this is so little. And actually if you wanted to know how much exactly is, it's an average. But my personal opinion is we're not going to use it because 78%, almost 21%, and this is almost nothing. This is not even 1%. So just to have an idea, you have a molecular weight in average of 29 grams of air per mole of air. So why bother to balance these 0.97% of other gases, which is noble gases plus CO2 plus water plus methane, many gases. Imagine how our mass balance will be. I don't think it's worth it, and it's very typically that in engineering we assume the composition of air as either as 0.79 fraction, which will be mole of nitrogen per mole of air, and the most important one, oxygen, 0.21 mole of oxygen per mole of air. We will be using this assumption in all the combustion problems, so forget all the 0.97% gases and just get used to this composition. Also, there's a relationship of nitrogen and oxygen, please know it. We told you before it's 21% of oxygen and 79% of nitrogen. The relationship, if we wanted to check it, will be simply that 0.79 mole of nitrogen exists per 21 mole of oxygen. So if we do this division, we will get 3.76 moles of nitrogen per mole of oxygen. So 1 mole of O2, you have 3.76 mole of nitrogen, and this is called 1 mole of air. So learn it if you can do it. The most important part is to learn this one, I think. This is a plus, this will help you a lot, but you need to learn this one. And when we talk about compositions, we will be talking about wet and dry base. What does this mean? It's simply a composition. When we say wet base, is a composition of a flow including water. So if we have water vapor or water as liquid or whatever, a humidity, and we account for it, for example, we have CO2 and we have CO and O2, now we have, let's see, water. If we do not count it, we only use this is dry base. But if we take water into account, we will be using this as wet base. Now, dry base is simply the composition of flow not including water. As I told you before, you just check this because you don't want to account water, and this is the dry base. And I'm going to show you some examples how to calculate dry and wet composition of air, because air, of course, has humidity. When it rains, the deserts also have air with humidity. It's low, yes, but we have humidity. So let's see. We have 1 mole of O2, 1 mole of N2, and 1 mole of water. They tell you please calculate the wet composition. That means we include water, so it's the total moles will be 3. We add them, it's 3, so 1/3 of each, 1/3 of each. This is the wet composition. But what happens when we only count for oxygen and nitrogen? We will add only 2, and it will be 1/2 and 1/2. H2O not included. So you can see the difference, 1/3 versus 1/5. Maybe you don't think that it's a lot, but it is. So keep practicing. Let's see more exercises. Dry versus wet base. Exercise number 1. They show you there's a gas, it contains 60% mole nitrogen, CO2, oxygen, and the balance H2O, which means is the difference. Calculate the molar composition of the gas on a dry basis. So we calculate 60%, 50%, 10%, and the other is 50%. If we add these, actually, we will sum or add 100. And let's choose a basis, which is 100, of course, 60, 15, 10, and 15. If we wanted just dry basis, we will need to add only these guys. Take out water. So dry is 60 plus 15 plus 10, which is 85. And we repeat. 60 divided by 85, 15 divided by 85, and 10 divided by 85. This will give you the new dry compositions, guys. So, of course, you're expecting to increase since we are taking out one component, everyone increases. Now, just to make you sure, let's do it in a wet basis. 60 divided by 100, 15 by 110, you will get the same percentage they give us, because of course we're doing it in a wet basis. Now, what happens when we want to go backwards from dry basis to, I don't know, to water and eventually calculate the amount of water? There's a special analysis which is called Orsat analysis. It's a technique for stacked gases which calculate the following compositions. They will give you how is the composition of a stacked gas going out of equipment, and they get you this. You know, you will add this is 100, yeah, this is 100. But of course there's humidity, there's water there. So we want to calculate this. A humidity measurement shows that the mole fraction of H2O in the stacked gas is this one. They tell you, please calculate the amount. Please calculate the composition on a wet basis. So let's choose a basis of dry air, 100 mole. We have this, and this. And yeah, if we want to check a wet basis, let's say we're going to have this equation. The total moles in a wet basis will be all the moles in the dry gas plus the wet component. And we know that all this here is 100, so it's 100, and we use X. So this is the total amount of air and water. And since we know, well, they give us the component here, the mole fraction of water. We know mole fraction by definition is mole of water divided by the total moles. We know mole of water, we choose this at X. And the total moles, we actually did this equation, so we can substitute it here. And they tell you this is equal to 0.07. This is nice because this we can turn it into one equation with one variable. We look out for X and we find out that X is, let me see, 7 divided by 0.93, and yeah, that's it. I think there's, just let me double proof it. 7 divided by 0.93, it's 73, something like that. No, 7.5, yeah. And then we go to calculate the total mass will be simply 100 plus the new water, which is 7, and you get this answer. Sorry guys, I didn't calculate the mass fractions, but it's so easy. You just need to check 65 divided by 107, and you go on 14, 11, 20, and X, which is 7.5 divided by 107, and you will have the composition. Okay, we're done with mass of water in the air. We're going to talk about the theoretical oxygen and excess oxygen, which is very simple actually. Many times there is an excess of oxygen to avoid incomplete combustion, because normally, yeah, if you have, I don't know, this, let's say it's a fuel, you want to cover it a lot from oxygen so it will not form incomplete combustion. So the more oxygen you put, I think they try to react easier, they have more exposure to oxygen, so they react better. So imagine this, we have methane and we have 4 moles of O2, and they will be producing 1 mole of CO2 and 2 moles of water. But the problem here is they could also, the methane could also react with 3 half of O2, which will give you 1 mole of CO. And that's not good because we can still oxidize more of this, and probably we will have more energy or heat. So if we use excess, imagine we use, instead of 4, we add 5 moles, we will probably not form CO because we have excess of oxygen, and you will form a nice CO2 and water combination. So, theoretical oxygen. It's the oxygen needed to perform a 100% combustion. Nice. Easy. For example, in methane, we need 4 moles of O2, and no, we need only 2. Let's do the mass balance. This is 1, hydrogen, you need only 2. Oh yeah, no, it's okay. Yeah, we need 4. So the theoretic oxygen is 4 moles of O2 to combust 1 mole of methane. Now, the excess oxygen is the oxygen that does not react after a 100% combustion, and it's always over. You'll have extra. So what happens when we add not 4 moles, but 5 moles of oxygen? You will be having also, I don't put it here because it's not that chemically correct, but you have 1 mole here left. So we use 4 moles for the combustion, and we have 1 mole that did not react. The excess oxygen is 1 mole. Now, we want to change these to percent, so it's easy. Excess oxygen, as I told you before, the oxygen you feed minus the oxygen you actually need divided by the oxygen you need. So for example, for a 20% oxygen excess in methane reaction will be 20% excess. You have these and these and these. So let's just find it, how much oxygen it will be. And you will find out that you want a 20% extra oxygen, you will get 4.8 moles of O2 instead of only 4 moles. So I hope you're getting the idea of what is excess of oxygen, because we're going to talk now about the excess of air. Since we use air to get oxygen to the reaction, we need to calculate air flows from oxygen. So you know 1 mole of O2 will give you certain moles, I think 4.3 mole of air in general. No. Anyways, there's a relationship. We're going to see it later. Theoretical air is the air needed to get the theoretical oxygen that we need. So we first need to check out how many or how much oxygen moles do we need, and with that we can calculate how much air do we need. But this is theoretical. Now the excess air is the air that goes extra, easier. It's almost the same as oxygen, but now it's air. And this will give us higher rates of combustion. And as seen before, it's similar to O2, because percent excess of air, it's the moles you feed of air minus the moles you must actually react divided by the moles of the same mole. This is the same quantity. Just be sure to have the same quantity. Times 100%, of course. Be aware of nitrogen content in air. Don't just add up oxygen. You need to add up nitrogen also, because nitrogen is 3.76 times the quantity of O2, so you will have a difference. So let's do this exercise. Easy. 100 mole of butane, which is here, and 5,000 mole of air per hour are fed into a combustion reactor. They tell you please calculate the excess air. So let's get the equation, C4H10, we balance it, and we have the coefficient 1, 13 halves, 4, and I think it's 5, no, 6, no, 5. And from this we know 1 mole of butane needs 13 half of moles of O2, so therefore 100 mole of B will be just this number times 100. So we have the theoretical moles of oxygen needed. Let's calculate the theoretical moles of air needed. So we know 1 mole of air contains 0.21 moles of oxygen, and we have 650 moles of oxygen. We just need to multiply, this go out, and you will find out that you only need 3095 mole of air, which is a little bit less than the 5000 we're feeding, so we are going to have definitely an excess of air. Let's calculate the excess is in minus required divided by the required. The inlet is 5000 mole of air minus the required, which is the one we calculated here, divided by this same number here. They will give you 0.61 or 61%. Good. Now we have two reactions, the one of incomplete combustion and the one complete combustion. I like it because you will practice the selectivity and in general how combustion normally goes. They ask you a lot. What is the theoretical O2 flow for a complete combustion? What is the theoretical O2 flow for only 70% combustion? And they tell you be careful, and I will show you why. Theoretical flow of air, easy. 100 excess air, how much blah blah blah, how much rate of air. Nice. And if the actual flow rate is 300 moles, what is the percent excess? So let's do it. First one is so easy. You just need 1 mole of methane per 2 moles of O2, which is here. So if you're using 100 mole of methane, you need 200 moles. Nice. Remember, we're feeding 100 mole of methane. Number 2, calculate the amount of oxygen required for a 70%. And this is tricky one. It's kind of like a joke because the definition of oxygen implies a 100% conversion. So the definition doesn't care how much the conversion is, because by definition you need to have 100%. So this is a tricky one, and you could not have a difference. The required oxygen will be the definition by 100%. So it will be the same, 200 moles. You need 200 moles. Number 3, they tell you how much air from this theoretical oxygen. That's easy one, just divide by 0.21, because we have 1 mole of air in 0.21 moles of oxygen, and you get this. Nice. Now they tell you have 100% excess. This is technically twice. Why? Please, hopefully you get to know that 100% implies twice. So we only multiply by 2. And we get 1904 moles of air. Now, we go to number 5, which is if we only have 300 mole of oxygen, how much mole of air will be extra? So you have this, we change it to air. 1 mole of O2 is 4.67 mole of air, and you get this value here. The excess will be simply the difference between this and the theoretical, and you get 50%. And that's everything for this exercise. Let me just show you the last tips for mass balancing combustion examples and problems. Please never ever forget nitrogen. Nitrogen is inert, I know, it doesn't affect, but it will affect the composition. And when you see energy balances, you will see that you will need to hit the nitrogen. So please guys, take care. Review the CO and CO2 balances. Always make sure the equations are balanced. And this is kind of tricky. If you have solved for nitrogen, be sure you're not producing SOx. or NOx. What is this? You could produce CO2, CO3, NO, NO2, NO2. You can produce a lot of these guys because at high temperatures they stop being, how do you say, they stop being inert, they start reacting with oxygen. And when you have oxygen in excess, review oxygen balance in the outlet gas. Typically you think all the oxygen converts to CO2 or water, but the truth is that when you have extra oxygen, you will have oxygen going out. And as a tip, I recommend you to learn the relationship between the moles of nitrogen per moles of oxygen. And once again, balance equation and double check the balance, guys. I think this is, yeah, I'm going to cut this video. We're going to see the next video, mass balance combustion exercises. What's up, guys? It's me, chemical engineering guy. So if you like the video, why not push the like button? It really helps me to know if you're liking the videos or if I should be changing something or I should be adding something, taking out content, whatever. Also, sharing is caring. So if you got any kind of friends, teachers, colleagues, or whatever kind of person that might be interested in this type of content, why not share it? Sharing helps our community to grow faster in members and in content. If you want to keep track of my activity, videos, uploads, experiments, playlists, whatever content I'm getting on YouTube, be sure to click the subscribe button. Subscribing to the channel is totally free, guys. My dream is to create an online academy of chemical engineering, where everyone can access it in the world. Imagine a place in which the student, the teacher, and the engineer get the best of each other. Thank you guys for the support and the love.